Chapter 7 Work and Kinetic Energy. Work. In physics, work is done on an object when energy is transferred to the object. In other words, work is done when a force acts on something that undergoes the displacement from one position to another. The simplest work to evaluate is that done by a force that is constant in magnitude and direction. In this case, we can factor out the force. The remaining integral is just the total displacement, which only depends on the endpoints. Figure B shows a person holding a briefcase. The person must exert an upward force equal in magnitude to the weight of the briefcase. But this force does no work, because the displacement over which it acts is zero. In Figure C, where the person in B is walking horizontally with constant speed, the work done by the person on the briefcase is still zero. But now, because the angle between the force exerted and the displacement is 90 degrees, vector F perpendicular to vector D and cosine 90 degrees equals 0. Kinetic energy. Kinetic energy is a property of a moving object or particle and depends not only on its motion but also on its mass. Network. Work done by all the forces acting on an object. The work-energy theorem states that the net work done by the forces on an object equals the change in its kinetic energy. According to this theorem, when an object slows down, its final kinetic energy is less than its initial kinetic energy. The change in its kinetic energy is negative, and so is the net work done on it. If an object speeds up, the net work done on it is positive. When calculating the net work, you must include all the forces that act on an object. Problem-solving strategy. Work-energy theorem. Step 1. Draw a free body diagram for each force on the object. 2. Determine whether or not each force does work over the displacement in the diagram. Be sure to keep any positive or negative signs in the work done. 3. Add up the total amount of work done by each force. 4. Set this total work equal to the change in kinetic energy and solve for any unknown parameter. 5. Check your answers. If the object is traveling at a constant speed or zero acceleration, the total work done should be 0 and match the change in kinetic energy. If the total work is positive, the object must have a sped up or increased kinetic energy. If the total work is negative, the object must have a slowed down or decreased kinetic energy. Power. Power is defined as the rate of doing work, or the limit of the average power for time intervals approaching 0. P equals dW over dt. Chapter 8 Conservation of Energy. Potential energy is the function of position energy possessed by an object relative to the system considered. The mechanical energy E of a particle stays constant unless forces outside the system or non-conservative forces do work on it, in which case the change in the mechanical energy is equal to the work done by the non-conservative forces. Problem-solving strategy. Conservation of energy. Identify the body or bodies to be studied, the system. Often in applications of the principle of mechanical energy conservation, we study more than one body at the same time. 2. Identify all forces acting on the body or bodies. 3. Determine whether each force that does work is conservative. If a non-conservative force, like friction, is doing work, then mechanical energy is not conserved. The system must then be analyzed with non-conservative work. 4. For every force that does work, choose a reference point and determine the potential energy function for the force. The reference points for the various potential energies do not have to be at the same location. 5. Apply the principle of mechanical energy conservation by setting the sum of the kinetic energies and potential energies equal at every point of interest.